about this? I don't think I did. Hi, welcome. Waiting for the stream to catch up. I'm extremely confused as to why my thumbnails keep getting deleted. It's a mystery. We'll handle it at another time. That's fun. The stream isn't actually starting. Let's try. Okay. YouTube is up. Hi, YouTube. Is Twitch up? It wasn't a second ago. Still ain't. There we go. All right. Hi. It is morning for me, so I'm going to say good morning. Good morning. Today I'm going to start a new paper, and I'm just realizing I did not tweet about this. But you know what? It's my usual schedule. I trust folks. We're going to be talking about this paper called The Elephant in the Interpretability Room, Why Use Attention as Explanation When We Have Saliency Methods. And it's by Jasmijn Bastings, or maybe Bastings? I don't know. And Katja Filippova? Again, I don't know. So if any of y'all know, please correct me and I will correct myself. Both out of Google research. So let's start with the abstract, and then I can talk a little bit about why I think this paper is particularly relevant to folks who are working in NLP, and specifically on conversational AI is the thing that I work on. Coffee. Abstract. There is a recent surge of interest in using attention as explanation of model predictions, with mixed evidence on whether attention can be used as such. While attention conveniently gives one weight per input token and is easily extracted, it is often unclear towards what goal it is used as an explanation. We find that often that goal, whether explicitly stated or not, is to find out what input tokens are the most relevant to a prediction, and that the implied user for the explanation is a model developer. For this goal and user, we argue that input saliency methods are better suited, and that there are no compelling reasons to use attention, despite the coincidence that it provides a weight for each input. With this position paper, we hope to shift some of the recent focus on attention to saliency methods, and for authors to clearly state the goal and users for their explanation. So, if you've been watching the Rasa YouTube channel for a while, you know that we have a lot of different videos where we talk about attentions. Transformer architectures right now are very widely used, and they are based pretty much entirely on this measure of attention. However, what the authors here are saying is that, hey, the thing that explainability research is trying to do is trying to have this measure that developers can use when they're working on a model that says, hey, this is the thing that was most important in making this decision. And they're going to argue that attention is not actually the most useful thing in that context, and that what is important is saliency. And I'm interested to see how they define saliency, because I've mentioned in previous streams, certainly in linguistics, saliency as a term is really overloaded. So it's used by a lot of different people in a lot of different ways to mean different but sort of related things. So when I was in graduate school, I had a whole seminar just on saliency and different ways of talking about saliency and measuring it. And it was more from a phonetic standpoint, because that was what my advisor was doing. But I think that this could be very useful for people who are working on models such as chatbots and need to be able to say, hey, this is why we decided, this is what this intent was. Or, whatever else it is that you're using. Introductions. There's no S, it just says introduction. Attention mechanisms, citation from 2015, have allowed for performance gains in many areas of NLP, including inter alia machine translation, natural language generation, and natural language inference. And this Vaswani et al. Paper is the transformer paper. So I will say, brief history, attention was primarily initially used with bidirectional LSTMs, long short-term memory, which were the predominant model in NLP and in NLP research at the time that this was introduced. So there's a pretty strong research cycle in NLP where a certain model or family of approaches will become very popular. People will write a lot of papers on it, and then something else will become popular, and people will focus on that in their paper writing, and so on. And this sort of cycle has, it's been going on since like the 60s. And just what it is that has been popular has sort of changed over time. And I think part of being an NLP researcher and being in the field is having sort of a general idea of what approaches were considered the best at different points in time and which might be the best for the particular thing that you're doing. Anyway, so attention been applied in a lot of ways. Attention is not only allowed for better performance, but also provides a window into how a model is operating. For example, from a Trine translation, Badenow, I think I'm saying that right, et al., 2015, visualize what source tokens the target token are attending to, often aligning words that are translations of each other. Whether the window that attention gives into how a model operates amounts to explanation has recently become a subject of debate. See section 2. While many papers published on the topic of explainable AI have been criticized for not defining explanations, the first key studies which spawned interest in attention as explanation in 2019 do say that they are interested in whether attention weights faithfully represent the responsibility each input token has on model prediction. That is, the narrow definition of explanation implied there is that it points to the most important input tokens for a prediction, argmax, accurately summarizing the reasoning process of the model. Jacobi and Goldberg, 2020b. So what they're saying here is that what attention can get you, if you have an input and an output sequence, and you're using an attention-based model, you can see which token which tokens in the input sequence had the most relation, using this attention measure, to tokens in the output sequence. And there's sort of this assumption in a lot of the explainability literature that means that the tokens that had the most intention had the most influence on the choice of the output token. But that's not necessarily the case, and that's what the rest of this paper is going to be. The above works have inspired some to find ways to make attention more faithful and or plausible by changing the nature of the hidden representation's attention. By changing the nature of the hidden representation's attention is computed using... I think it's by changing the nature of the hidden representation's attention is computed over using special training objectives. Sorry, I'm having trouble parsing the sentence. Changing the nature of the hidden representation's attention is computed over using special training objectives. Okay, I am having trouble parsing that. Yeah, I'm just having trouble parsing that sentence. Others have proposed replacing the attention mechanism with a latent alignment model. Okay, so one way to make attention actually be more faithful to what's being used to make the decision is to change the way the hidden representations are computed. The attention for the hidden representations is computed. Okay, I'm picking that up. Or replacing the attention mechanism with a latent alignment model, Deng et al. 2018. And that would probably be with an LSTM, because I don't know how you would replace the alignment I don't know how you would replace attention and transformers. I mean, it would be, at that point, it would be a different model. Interestingly, the implied definition of explanation in the cited works happens to coincide with what input saliency methods are designed to produce, section 3, and then a bunch of citations. Moreover, the user of that explanation is often implied to be a model developer, to which faithfulness is important. The elephant in the room is therefore, if the goal of using attention as explanation is to assign importance weights to the input tokens in a faithful manner, why should the attention mechanism be preferred over the multitude of existing input saliency methods to do exactly that? So if what you need in explanation is, hey, I made this decision, here was what was most important to me in making this decision, the assumption that underlies a lot of sort of the attention methods is that that's what attention is doing, but it's not necessarily the case, and there are methods that do that. So I think the way saliency is being defined here is what input tokens are, or features, most affected the output decision, right? In this position paper, with that goal in mind, we argue that we should pay attention, no heed. Section 4. We propose that we should reduce our focus on attention as explanation and then shift it to input saliency methods instead. However, we do emphasize that understanding the role of attention is still a valid research goal. And finally, we discuss a few approaches that go beyond saliency. So attention, fairly new-ish in terms of like NLP techniques. What does it do? There's this assumption that it's telling you what's most important. May not be the case. There are methods that do tell you what's most important. What does attention really do? Open research question. That's the paper. And position papers are a form of academic paper that's like, hey, this is what I think on a specific topic. So it's not necessarily always like a, hey, here's this project I did, here are the results. It's like, hey, this is what people are doing in the field, and we think that that either like they should keep doing it, but in a slightly different way, or they should do something else, and that would be more helpful. Yeah. And so I would say, to answer the question about why are people using attention, with a lot of modern NLP methods, you already have attention, so you don't need to calculate anything additional. So it's just sort of like the easiest solution would be my guess as to why people are doing it. Robbie says, input token, do you mean X1, X2, X3 to neural network? So input token here, for something like machine translation, it would be like, input tokens would be each of the tokens in the input sequence. So for example, le chat est gros, the cat is fat, would be the tokens in the input sequence, and then translating it to English, the cat is fat would be the tokens in the output sequence. And from an attention perspective, you would probably expect more attention on chat and cat when you were deciding what to say for that word. Not that machine translation work by word transliteration. That's actually an extremely bad approach to translation. Yeah, to sort of answer your questions. Quarky, I thought salience was a concept specific to image. Oh, very much no. What does it mean in this context? So the way that it's being narrowly defined here is what input tokens have the most influence on the output tokens. That makes sense. Vasulolber, I have no idea how to say that, says, I never understood any research paper. Hopefully I won't understand this as well. You might surprise yourself. Habib, the stream's title only shows Rasa Reading Group. So it do. The title should be Rasa Reading Group, the elephant in the interpretability room. I don't know what happens if I edit something while it's live. Thanks. I'll try and fix that after the stream. So there are methods that will tell you what was important to making the decision. Attention is not necessarily one of those methods. More details. The attention debate. In this section, we summarize the debate on whether attention is explanation. The debate mostly features a simple bi-LSTM classifier, so bidirectional long short-term memory. It's a type of recurrent neural network that forgets things. It's just like a dumb way of putting it. Unlike transformers, they only contain a single attention mechanism, which is typically MLP-based, multi-level perceptron. I don't know that we need to. No, all right, well, they talk about it. So AI is the attention score for the bi-LSTM state HI. So this is the internal representation of the token at this sequence. The token at this point in the sequence. Where there is a single input text, there is no query, and Q is either a trained parameter like V, WH, and WQ, or WQQ is simply left out of equation 1. All right, let's break this down a little bit because I think this will be helpful going further. Attention means giving weight importance to the word, I guess. So attention is this, right? This that we're looking at right here, this alpha sub I. It is a specific technique, I guess. It's a specific like mathematical construction, and it has the same name as human thing that humans do. That is a word that we use in a general context, but it has a specific definition. Hi, Diraj. I don't understand. Nobody can understand researchers. I think you might surprise yourself. Okay, so we have, so this model is for this sequence of tokens. We have a sequence of hidden states that give an attention output, and then we are summing over that output, and that gives us our so these are all intermediate states. So the input would be these x's and the output would be the y. So this could be, for example, a sentiment model. So the output would be probably positive sentiment. So for each of these, so I don't think this is an E. I think this is an epsilon. All right, so we have V. I don't know what this fat V means. And then transpose tan. And this is the query. Q is either a trained parameter, and WH is the I'm digging through my oatmeal brain. I know I knowed this at one point. What is this research paper about? Very broadly, what method should you use to understand what information a model is using to make a decision? Learning the jargon makes it easier, definitely. Yeah, I mean, research papers are written for other researchers, and the assumption is that you're working in the field and you have an understanding of this shared vocabulary. Diraj says, I think it's just a method to force a model to give weight to some words related to the task. So it definitely gives weight to some words. Whether the degree to which they're related to the task and what that relation is sort of the question that the this paper is looking at. Is this a new Google multilingual model? No, it's a position paper. So they're like, this is where we think the direction of research in the field should go. All right. Anyway, so when we say attention, this is specifically what we mean. So this is, I believe, EI. So for A, we're going to calculate this for the input word and some trained query parameter. So this is just like another matrix or a vector that is trained and updated as the model is updated. All right, is attention not explanation? Jane and Wallace show that attention is often uncorrelated with gradient-based feature important measures, and that one can often find a completely different set of attention weights that result in the same prediction. So this is experimental evidence that the attention weights that you get for a specific what's a good way to put this? So there are different ways that you could use the information that you're given. There are different weights that you could give to each piece of information. And if you are using a feature-based importance measure, which does say, hey, which feature is the most like discriminative in this case, the attention is not necessarily going to correlate with the feature importance. And for a given input and output, you might get the same answer with a different apportionment of attention. So there's not like a single answer for what your attention weight should be for a specific problem to get the best output. And because it's learned, and it's learned using a method that there's sort of like, probability associated with, you're not always guaranteed to get to, the same attention weights, and the same model trained in the same way on the same data might end up with different attention weights for the same output, if that makes sense. Because you're being rewarded for the attention weights. Sorry, you're being rewarded for the final output. The model does not receive feedback on the intermediate states if you're using, gradient descent. In addition to that, Serrano and Smith find by modifying attention weights, they often do not identify those representations that are most important to the prediction of the model. So here they just changed attention weights and changing the weights didn't reliably affect the prediction. However, Poigraf and Pinter claim that these works do not disprove the usefulness of attention as explanation per se. So it's not a reliable explanation, and the relationship between the attention and the output is not necessarily always clear, but they claim that you can use, these authors claim that you can use attention as a way of doing model explanation, and that they offer some tests for it. And one of it is they are able to find alternate attention weights using an adversarial training setup, which suggests attention is not always a faithful explanation. So different attention weights, same output, I'm guessing. Adversarial means that they're lying to the model in a way, intentionally lying to the model in a way that's intended to trick it. Yeah, I'm not entirely following the argumentation here. I might need to go read that paper. Finally, Prithia et al. 2020 propose a method to produce a deceptive attention weights. Their method reduces how many weights are assigned to a set of impermissible tokens, even when the models demonstratively rely on these tokens for their predictions. So, for example, if you're trying to show that, your lone flagging model is not using race, you'd say, hey, don't pay attention to these race correlates, even if the model actually is using those race correlates, just as an example. All right. I barely know myself. Try to follow some researchers on Twitter's. Rachel paper reading streams are amazing to get started. You just have to attend regularly. Oh, thank you. I'm glad I can help. Yeah, I mean, I learned to read research papers by reading a lot of research papers in grad school. It's just sort of the way that you got to do it. Was the right task analyzed? In the attention as explanation research to date, text classification with LSTMs received the most scrutiny. So that would be something like, intent classification or sentiment analysis, things like that. However, Bastings et al. 2019 question why one should focus on single sequence tasks at all, because the attention mechanism is arguably far less important there than in models involving two sequences, like natural language inference or machine translation. Indeed, the performance of a neural machine translation model degrades subsequently if uniform weights are used, while random attention weights affect the text classification performance minimally. Therefore, findings from text classification studies may not generalize to tasks where attention is a crucial component. So if you're doing anything where you have an input sequence and then the output is also a sequence, attention may be much more important than if you have an input sequence and an output picking from a class. Interestingly, even for the task of machine translation, the first case where attention was visualized to inspect a model, Ding et al. 2019 find that saliency methods yield better word alignments. Okay, so attention might work a little bit better in sequence-to-sequence models. Even in those sequence-to-sequence models, though, using a method designed to figure out which features were most influential do better. Is a causal definition assumed? Grimsley et al. Go so far as saying that attention is not explanation by definition if a causal definition of explanation is assumed. Drawing on the work in philosophy, they point out that causal explanations presuppose that a surgical intervention is possible, which is not the case with deep neural networks. One cannot intervene on attention while keeping all other variables invariant. I don't think that is, okay. I should first of all say, I don't have a philosophy background in causal stuff. I do have a little bit of training in causal modeling. And you definitely can have covariates in causal modeling. So the big goal of causal modeling is if you have, you know, a graph structure. So let's say you have mortality as your output variable and all of these things that might be input variables. You want to be able to draw a line between, you know, X and Y. X definitely affects Y, and say, hey, we're pretty sure that there isn't like this separate latent variable that also affects Y that depends on X. That is causing the change, and that it's actually all happening in this latent variable and not because of this variable that we're saying is causing Y. So I don't, right? So that's a slightly different question than, hey, can I change this one variable and will that change everything else? Or without changing anything else, right? But again, I'm not super deep in the philosophy, so that could be like the standard interpretation of causality. 2.4, can attention be improved? The problems with using attention as explanation, especially regarding faithfulness, have inspired some to try and improve the attention weights to make them more faithful and or plausible. Mohan Kumar et al. Observe high similarity between the hidden representations of LSTM states and propose a diversity-driven training objective that makes the hidden representations more diverse across time steps. Let me run that by myself again. High similarity between the hidden representations in LSTMs and propose in states. Okay, so they're looking at different states of the LSTM, the hidden representations. These guys look very similar, and propose a diversity-driven training objective that makes the hidden representations more diverse across time steps. Gotcha. Okay, so over time, if you look at the hidden representations as you're stepping through the sequence, they're very stable. Can we make them more different over time and therefore get in, you know, maybe more explanatory power? They show that using representation erasure, they show using representation erasure that the resulting attention weights result in decision flips more easily as compared to vanilla attention. Okay, so if we sort of remove representations, we can see that causing the weights to be more diverse causes an easier change in the final output. With a similar motivation, Tutek and Snyder? I'm sorry, I do not know about that one. I apologize. Use a word level objective to achieve a stronger connection between hidden states and the words they represent. Well, which affects attention? Okay, so there's a word level objective, right? So this, you know, final output, there would be one for each word that you are also rewarded for doing good on, which affects attention. Not part of the recent debate, Deng et al. 2018 propose variational attention as an alternative to the soft attention of Badenow, arguing that the latter is not alignment, only approximation thereof. I don't know what the difference between variational and soft attention is. I'm sure these papers explain it. They have the additional benefit of allowing posterior alignments conditioned on the input and output sequence. Okay, so posterior, like after the inference is done, here's the input sequence, here's the output sequence, give me the alignment that seems most reasonable. I think it's what they're saying there. Saliency methods. In this section, we discuss various input saliency methods for NLP as alternatives to attention: gradient-based, propagation-based, and occlusion-based methods. Following Rasa et al. 2019. We do not endorse any specific method, but rather try to give an overview of methods and how they differ. We discuss methods that are applicable to any neural NLP model, allowing access to model internals, such as activations and gradients, as attention itself requires such access. We leave out more expensive methods that use a surrogate model, e.g. LIME. So LIME is a really, it is a pretty well-known explanatory model. Let's see this footnote. For an evaluation of methods for explaining LSTM-based models, see Pointer et al. 2018 and Aris et al. 2019. All right, gradient-based methods. When used earlier in other fields, Lee et al. Used gradients as an explanation in NLP and compute. All right, the upside down delta. I don't think that's a delta. Is that a gamma? That is. For a function c of x1 through xn, where xi is the input word embedding for a time step. Okay, so you're looking at all of the time steps, you're applying this function over it. And fc x1n is the model output for target class C. Okay, so this is what the model says about class C, given all of the words of the time step. And then I'm guessing that's, and then you compute the gradient. Oh, I see. Okay, so if you're word at your time step, you have all of the information about the model class, and then you have this one. I don't know what letter that is. Oh, upside down triangle. Let's see. I was checking to see if anyone in the chat knew what the upside down triangle was called. After taking the L2 norm of equation 2, the result is a measure of how sensitive the model is to the M input at time step I. Okay, so how much would changing the input at time step I change how quickly and in what direction the model changes, I believe is what that's saying. If instead we take the dot product of equation 2 with the input word at embedding xi, we arrive at the gradient times input model, Dunn et al. 2015, which returns a saliency scalar input, a saliency scalar of input I. So here we are, we have the this saliency measure, and then we have also the word embedding for the I, and we take the dot product, and that gives us not a single number, but multiple numbers. Does this give us a single number? I don't know. Trog says delta. I thought delta was the other way around. I'm also very dyslexic, so don't trust me about object rotations and flipping. Okay, maybe that is delta. Integrated gradients, IG, Sundararajan, I think, sorry, is a gradient-based method which deals with the problem of saturation. Gradients may get close to 0 for a well-fitted function. IG requires a baseline bi through n, e.g. all 0 vectors or repeated mask vectors. Okay, so here we are summing over this delta, and let's see which was, so M is gradients for each of our gradients, with the inputs to FC being linearly interpolated between the baseline and the original input x1 in M steps. Okay, so we sort of like step down through the gradient that we're tracing using a number of steps that's defined here. We then take the dot product of the averaged gradient with the input embedding xi minus the baseline. Okay, so basically, how far did the input token xi move the model over time? And is this the average? Yeah, so how big was the average step for this particular input thing, right? So what they're saying is, hey, if you start doing really well approximating a function, eventually you're going to get to sort of like, you know, the bottom of your gradient, and let's say it's parabolic, and you're not gonna like, you're just gonna go very tiny little steps, because the gradient's very like flattish. So what we care about is, hey, over the course of training, how much did this cause movement in the overall gradient is the difference there, I believe. Make sure I'm scrolled all the way down. Yeah, agreement that it is delta. Thank you. Yeah, we average over the gradients. Okay. We propose distinguishing sensitivity from saliency following Ancona et al. 2019. The former says how much a change in the input changes the output, while the latter is the marginal effects of each input word on the prediction. Okay, so sensitivity is if I change something, how likely is it to change the output? And saliency is, hey, looking at all of our input words, which one had the greatest effect on the output? So I could be very sensitive to something that doesn't have a lot of saliency, right? So if I was looking at, I'm trying to come up with a good example of this. It's a little counterintuitive. So maybe something like, gosh, I don't know, like two names, like Jim hated the movie and Jack hated the movie. Maybe Jim always hates movies. So changing the name would change the or like Jack didn't mind the movie, Jack didn't like the movie, Jim didn't like the movie. Jack always hates movies, so for him, didn't like is a positive, like if you switch the name, for him, didn't like would be actually a positive measure. And for, I could come up with better names, A and B. So A always hates movies, so for that person, didn't like becomes like a positive sentiment, like it's the most positive sentiment that that person's willing to give. B usually likes movies, so switching that person, that's actually a really negative sentiment. But didn't like is probably going to be the thing that has the most weight on the prediction, if that makes sense. I don't know that that's a great example. Yeah. What article book are we reading? That's a great question. We are reading the article, The Elephant in the Interpretability Room, Why Use Attention as Explanation When We Have Saliency Methods by Bastings and Filippova. That may not be how either of those names are said. Gradients measure sensitivity, whereas gradients by input and IG measure saliency. So IG is this integrated gradients measure. Okay, so how much has it changed over time? Saliency. A model can be sensitive to an input at a time step, but it depends on the actual input vector if it was important for the prediction. Okay, so a model can be sensitive to an input at a time step, but it depends on the actual input vector. Okay, so if like I'm waiting for the word like really hates for my sentiment analysis, if I don't see it, even though that's very important, it's not going to change my opinion, I think is what they're saying here. These are very closely related concepts. Talk says overfit on the wrong time step feature. Yeah, like what if we saw this feature, it would change our opinion, but we didn't see it right now, so we don't care that it would have changed our opinion, I think is what they're saying here, would be another way of saying this. Okay, propagation-based methods. Propagation-based methods, examples of which we discuss layer-wise relevance propagation. In particular, start with a forward pass to obtain the output FFC for X1, so the classification given each of the input tokens, which is the top level relevance. They then use a special backwards pass that at each level redistributes the incoming relevance among the inputs of that layer. So you have your classifier, and then they're going to go back down through the model, and every time they hit a new layer in the model, they're going to be like, okay, here's all the relevance. I'm going to assign it, down, assign it, down, assign it. Each kind of layer has its own propagation rules. For example, there are different rules for feed-forward layers and LSTM layers. Relevance is redistributed until we arrive at the input layers. While LRP requires implementing a custom backwards pass, it does allow precise control to preserve relevance and has been shown to work better than using the gradient-based methods on the text classification. Okay, so this is like a top-down approach where you have the classification and then you go back down to the model and you're like, all right. Well, here's, everybody gets a little bit, and you get more if you were more influential, I guess. And then at the end, you would have like that measure for each of your input tokens. Occlusion-based methods. Occlusion just means hiding. Compute input saliency by occluding or erasing input features and measuring how that affects the model. Intuitively, erasing unimportant features does not affect the model, whereas the opposite is true for important features. Lee et al. Erase word embedding dimensions and whole words to see how doing so affects the model. So this is something that people have been doing a lot with things like BERT, where you slowly start like knocking chunks off the model and see how it do. And for transformer models in particular, you can knock off a lot of the model before it stops doing good. They compute the importance of a word on a data set by averaging how much for each example erasing the word caused a difference in the output compared to not erasing that word. Okay, so this is not in the input. This is in the entire data set. So for the saliency example, removing like the word, hated from the entire data set. I guess you would have to, different output. I guess you'd have to retrain every time you knock a word out. I'm not entirely sure how that works. As a saliency method, however, we can apply their method to a single example only. Oh, this is how it works. For the input, you take the classification and then you remove the classification where you set the token to all zeros. Indicates that the input word embedding was zeroed out while the other inputs were unmodified. So you do a pass through your model where instead of your usual word embedding for the word that you're interested in, you set it all to zeros. I think of these methods, this is the one that makes the most intuitive sense to me. The mask uses n+1 forward passes, so you have to do it once for each word. It is also used for evaluation to see if important words another method has identified bring a change in the model output. Okay, so this is also a way to be like, the backpropagation was like, hey, we think this is the most important word. Does changing or does removing the embedding for that word actually change the model output? Hi, old player. Okay, that makes sense. Wow, we are breezing through this paper. Saliency versus attention. So attention is this word-wise, or I guess token-wise measure that gets all squished together, and then you get, for this one, a single model out. The authors suggest that based on previous work, having the attention measure and then output, instead of doing softmax over everything and getting your classification out, doing this on a sequence to sequence task. So you have x1 through x4 out, and then y1 through yi out, and then that's a more relevant way to use these attention measures or saliency measures. And then saliency is all of the things that we just talked about in terms of the different things that, all of the different methods that we just talked about are different ways of doing saliency. So the zeroing outwards, the going back through the model and assigning weights. They're not really weights. I shouldn't say that because they're not changing weights. The assigning this measure of relevancy, and then these gradient-based methods where you peek at the gradients. Saliency versus attention. We discussed the use of attention as explanation and input saliency methods as alternatives. We will now argue why saliency methods should be preferred over attention for explanation. In many of the cited papers, Whether implicitly or explicitly, the goal of the explanation is to reveal which input words are the most important ones for the final prediction. This is perhaps a consequence of contention computing one weight per input, so it is necessarily understood in terms of those inputs. So what we're trying to do is like, hey, what words are important? The intended user for the explanation is often not stated, but typically that user is a model developer and not a non-expert end user, for example. This is something we've talked about quite a bit, sort of like at Rasa, as well as like who would model explainability measures be helpful for. For model developers, faithfulness, the need for an explanation to accurately represent the reasoning of a model, is a key concern. You do not want to tell your stakeholders incorrect things. On the other hand, plausibility is of lesser concern because a model developer aims to understand and possibly improve the model, and the model does not necessarily need to align with human intuition. Say Jacobi and Goldberg for detailed discussion of the differences between faithfulness and plausibility. So I think if you have a faithful representation of your model inputs, and also it seems to align with how a human would make a judgment, that is very satisfying, especially to non-technical stakeholders. But I agree. Like, I would rather really know what's important than be lied to and told, oh, yeah, it's the same features you'd use. Yeah, it's fine. Yeah. So I think that's a really good point to pick apart. With this goal and user clearly stated, it is impossible to make an argument in favor of using attention as an explanation. I mean, I think it's possible. I don't think they'd necessarily be great arguments. Input saliency methods are addressing the goal head on. They reveal why one particular model prediction was made in terms of how relevant each input word was to that prediction. Okay, so input saliency is like, hey, there's different methods of doing this. We're pretty sure that this is like how much this word affected the output. They reveal why one particular, I just said that. Moreover, input saliency methods typically take the entire computation path into account, all the way from the input word embedding to the target output prediction value. Attention weights do not. They reflect, at one point in the computation, how much the model attends to each input representation, but those representations might already have mixed in information from other inputs. Okay, so they're saying that, like, going back to this little figure, if you are looking at attention, right? Yes, attention has, you know, a one-to-one relationship with the input, but that doesn't mean that there aren't, you know, excuse me. That doesn't mean that there aren't intervening causal links, especially with something like a bidirectional LSTM, where the hidden state has input from both things that occur after it and things that occur before it. H2 would probably be a better example there. Or in a transformer, where each attention state has influence from everything else in the window at the same time. So if you go back and go all the way back down to the input token, then you have a much clearer idea of the influence of the input token. If you're using sort of this intermediate state, hidden state, attention measure, you're not going to necessarily be getting the full story. You're going to be getting, you know, a snapshot of the process. It's a good point. That's a really good point. I think that also has maybe some, there's been a lot of work I've mentioned on sort of transformer models and looking at grammatical stuff and where the attention is apportioned to those things, but that is very much an intermediary step, the attention in those transformer models. So yeah, I wonder what, so if you take this to be true, I wonder how that affects your stance on Bertology. So the study of these models and how they affect each other. Or how they're representing information. I says, do again, please. Not sure what you're talking about. Okay. One might argue that attention, despite its flaws, is easily extracted and computationally efficient. Yeah, so the thing where I said earlier, like, people are using attention because it's easy to use attention. I am all about efficiency. I am all about as few steps as possible, you know, effective engineering through laziness. But if you want to be sure, I think the authors are arguing here that shortcuts are gonna bite you. However, it will only take one line in a framework like TensorFlow to compute the gradient of the output with regard to the input word embeddings, so implementation difficulty is not a strong argument. In terms of efficiency, it is true for attention only a forward pass is required, but many of the other methods discussed at most require a forward and then a backward pass, which is still extremely efficient. So forward pass just going through the model from the input tokens to the output, backward pass going back through the model from the output tokens back to the input. And they're not, like, these attention measures aren't trained, right? So like the backpropagation just like goes through. It doesn't require like developing a model that learns how to do that over time. Quarky says, I've never heard Bertology before. Yeah, it's there might be a workshop called Bertology. It's just sort of an informal term that NLP researchers use to talk about the people who are looking at the inner workings of BERT. I don't think there's one for GPT-3. I mean, the model ain't released, so that's one thing. And also it's kind of basically the same model. No, that's not true. There are some differences between BERT and GPT-3, but they are very, very similar. So a lot of the things that hold for BERT should also hold for GPT-3. Or sorry, a lot of GPT-3 is very similar to GPT-2, which has been released. And there's honestly just been less work on it than BERT. Despite the hype, like, researchers tend to pay more attention to BERT. And I realize there's obviously a lag, but GPT-2 came out before BERT, I believe. So folks had time. Yeah. Anyway. So it doesn't take that long, is what they're saying here. Attention is not interesting. In this position paper, we criticized the use of attention to address input saliency for the benefit of a model developer. We emphasize that understanding the role of attention mechanism is a perfectly justified research goal. For example, Voida et al. And Michael et al. Analyze the role of attention heads in the transformer architecture and identify a few distinct functions they have. And Struble et al. Train attention heads to perform dependency parsing, adding a linguistic bias. So we talked about these papers in the in Anna Rogers' paper that we read a while ago. I mean, while doing stakeholder, that's gesture. Yeah, I gesture a lot. And a sequence-to-sequence model, BERT model are similar. Is sequence-to-sequence model and BERT model similar? Yes. So there's a video in the NLP for Developers playlist on BERT that I did that goes a little bit more deep into it. But BERT is basically the first half of a sequence-to-sequence model. Trog says the paper title, A Primer in Bertology. That's the Anna Rogers paper I was mentioning. Opong says, just found out you guys exist, big learning curve, but I'm excited to learn and thank you for all your hard work. Oh, welcome. Happy to have you. Do I know all researchers? Nah. But I mean, I have a research degree. I have a PhD, and a big part of getting a research degree is becoming part of the research community. So I think this is something that's not necessarily obvious if you haven't worked in research, but any, scientific engineering discipline, things are really a conversation, right? So person A will say something, person B will respond to them, person C will respond to A and B, person D will respond to A, B, C, and so on and so forth. So understanding sort of the work that's been done before and who's doing that work. Like, you don't need to know the people individually, but if you're working on something, and particularly in NLP where the main publication venue is conferences, it's pretty common to, meet the same people at workshops all the time. So I've met most of the people who work on computational sociolinguistics, because that's what I was working on, or at least who were in 2017. I don't go to as many conferences these days. Anyway, we're all on Twitter these days anyway. No one's going to physical conferences. We also stress that if the definition of explanation is adjusted, for example, if a different intended user and a different explanatory goal are articulated, attention may become a useful explanation for a certain application. For example, Stroud et al. Demonstrates that supervised attention helps humans accomplish a task faster than random or unsupervised attention. for a user and a goal that are very different from those implied in section 2. And for me, as as a developer, I want to know what features were important, and I agree that, I am the target audience that they're talking about in this paper, so I find this pretty helpful for me. Can I publish a research paper without any PhD after a master's? Yep, but a PhD is training in how to write research papers and do research. So I think you're more likely to get a paper published if you have a PhD, just because you have that training. Any tips on getting started for people who don't have a degree in research? It's hard. I would say start by doing an introductory course so you have an idea of the background of the field. Liza says, does Rasa have an entity extractor for date like Duckling do? We recommend you use Duckling. So just, I should say just. So we recommend that you use a Duckling server. Duckling, if you're not familiar, it's project for removing, information from text and making it more structured. So things like dates, times, it does URLs, it does credit card numbers, that sort of very structured data, which you could do using regular expressions you build yourself, but that's why I wouldn't recommend that. All right, is saliency the ultimate answer? Check how much we have left in this paper. Oh, we're gonna finish this. Is saliency the ultimate answer? Beyond saliency, while we have argued that saliency methods are a good fit for our goal, there are other goals for which different methods can be a better fit. For example, counterfactual analysis may lead to insights aided by visualization tools. So counterfactual analysis, changing something and seeing what happens, basically. The diff mask method of Takao et al. Adds another dimension. It not only reveals in which layer a model knows which inputs are important, but also where important information is stored as it flows through the layers of the model. Other examples are models that rationalize their predictions, Lee et al., Bastings et al. I think this is usually done as multitask learning, so you generate the prediction and the explanation at the same time, which can guarantee faithful explanations, although they may be very sensitive to so-called Trojans. And I think this is a, I'm not familiar with this paper, actually. This sounds like it might be a adversarial method. I did some research with a bachelor degree. Is that enough, or must it be a PhD? You do not need a research degree to do research, but a PhD is training in doing research. So if you're working on stuff and it's, motivating to you and interesting to other people and, well-founded in the stuff that came before, then there's, you don't need a PhD to do research, but again, it helps, register for NeurIPS. NeurIPS is a lot. So NeurIPS is Neural Information Processing Systems. It's the biggest sort of deep learning conference. If you're specifically interested in NLP, I might recommend going with an ACL conference, the Association for Computational Linguistics, and I think the next one is EMNLP, because it'll be a little bit more focused. But if you're interested in deep learning generally, NeurIPS is a big one. Yeah. I use Duckling, but the Docker that runs Duckling keeps failing. Yeah. I would say ask on the forums and provide sort of like your image so that folks can take a look. Limitations of saliency. A known problem with occlusion-based saliency methods, as well as eraser-based evaluation of any input saliency technique, is that changes in the predicted probabilities may be due to the fact that the corrupted input falls off the manifold of training data. Oh, interesting. Oh, I wonder if this is Sarah Hooker. It is Sarah. Sarah's great. Okay, so what they're saying is, hey, if you replace one of these embeddings with zeros, you are creating a situation that your training data has never seen. And if you sort of like have this decision region, suddenly all zeros would go boop, completely off of that. That is, a drop in probability can be explained by the input being out of domain and not by an important feature missing. It has also been demonstrated that at least some of the saliency methods are not reliable and produce unintuitive results or violate certain axioms. I would say that it would be okay to get unintuitive results as long as they are faithfully representing what the model does. A more fundamental limitation is the expressiveness of input saliency methods. Obviously, a bag of per token saliency weights can be called an explanation only in a very narrow sense. One can overcome some limitations of the flat representation of importance by indicating dependencies between important features. For example, Janicek et al. 2020 present an extension of IG which explains pairwise feature interactions. But it is hardly possible to fully understand why a deep, nonlinear model produced a certain prediction only by looking at the input tokens. Yeah, this is a really good point. So all of these methods that are like, discuss how or summarize how the input tokens affected the output are an approximation of why a model is doing things. Yeah, that's a good point. I'm enjoying this paper. It's a good paper. So based on these limitations, going back to the saliency methods they mentioned, so this last one where you zero things out, oh god, that seems like the easiest to implement, but sounds like you might run into some potential problems there, where the answers that you get, you're getting because things are out of domain. And this one as well, the IG method where you remove the information from an all zeros or sort of like mask vector, I think also has the potential to get things that are out of domain. So it might be these propagation-based methods, even though they sound the hardest to do. I mean, you could probably use the propagation rules here for the feed4 layers and the LSTM layers that somebody else has already created. It sounds like this one might have the most ecological validity, so might be the best representation of the information as a whole outside of your specific training debt. I was gonna say maybe the occlusion-based methods are the one that I would use, again, because it's the simplest, but if they have that sort of really big drawback, it might be worth it to spend a little bit more time on the propagation-based methods. I'd probably also, recommend reading at least one of these papers or skimming one of these papers or seeing if you can find the code for one of these papers before implementing it from scratch. Conclusion. We summarize the debate on whether attention is explanation and observe that the goal for explanation is often to determine what inputs are the most relevant to the prediction. The user for that explanation often goes unstated, but is typically assumed to be a model developer. With this goal and user clearly stated, we argued that input saliency methods, of which discussed are a few, are better suited than attention. We hope, at least for the goal and users that we identify, that the focus shifts from attention to input saliency methods, and perhaps to entirely different methods, goals, and users. And then acknowledgements. Okay, so basically, all right, we get it. You've got the attention weights already. They're there, they're easy, but they're not necessarily going to be giving you the answers that you need. So if you care about an explanation on an input token level basis about which tokens are affecting the model decision, it's worth it to spend a little bit of extra time doing the saliency methods. And even though it might take a little bit of extra time to set up, they're not going to be that much more time. So they'll be like, maybe twice as much time to run as the attention methods, because the attention methods go, up through the model once. The saliency methods go, at most up through the model once, back through the model once. So, yeah. Questions? Does Spacey provide the entity extraction? Spacey does named entity extraction, which I don't know that they have a built-in for dates and stuff like that. Douglas says, thank you for the answer, but I think I should be more writing a portfolio and doing individual research to convince people and get a better job. I'm currently learning some machine learning and data science things. Yeah, I mean, if your goal is to work in industry as a data scientist or a machine learning engineer, you do not need to do research. It is not a requirement. Job requirements that are like, oh, you got to have a paper published in Europe. That's ridiculous. That's completely unnecessary. And I mean, to be perfectly honest, if you submit a paper to a conference, it gets reviewed by researchers. And if you don't actually care about doing the research and getting a paper submitted, except as like a goal to help you with your career advancement in a career that's not research, it's kind of a waste of folks' time. Like, I mean, if you have a project that like you want to share and you think is important and you think you're doing new and exciting stuff and you have, you know, again, good grounding in the other related research, then by all means go ahead. I don't want to discourage you, but don't feel like you have to write a research paper just to write a research paper, you know? Yeah. Does building a custom model pipeline take a lot of time? So talking about Rasa, if you just are, you know, using pipeline components and putting them in your domain file or config file and then retraining your model, no, it shouldn't. If you are completely building something completely from scratch and you're training your own representations, it can take a little bit longer. It depends. It depends on your experience. It depends on your hardware availability. Yeah. He says, oh, thank you. Yeah, I hope that's helpful. I don't know. I know that there's this weird thing where people were looking for like engineers and like, you have to have a research paper, and they're different jobs, y'all. They're extremely different jobs. I don't know. So yeah, I think I certainly enjoyed reading this paper. I'm convinced by a lot of the points that they make. I don't know about this paper. Grimsley et al. Why attention is not explanation, surgical interventions, and the causal reasoning about neural methods at LREC 2020. Yeah. I don't know. I'd have to read more about that paper. That's the section that I was most like, I don't know. But I will also say that I took one causal modeling class 5 years ago. So I'm a tiny bit rusty. I haven't done a whole bunch since then. Yeah, but that's how I remember causal modeling. So if I think the big recommendation from this paper is, hey, if you're a developer, you're working on a model, you need to be like, hey, I'm pretty sure this is why the model made this decision here. A saliency method is going to be better than just pulling the attention weights. And there are some options, the options of looking at the gradients, the options of doing a backwards pass through the model to apportion the relevance, or the option of zeroing out some weights, doing the zeros and going through their whole input sequence, and then getting the differences of the model output out. Great. Ashu says, I recently got a job offer with my organization for deep learning role. I need to learn a lot of things. Oh, congrats. Yeah, can definitely be overwhelming when you first come into the field. And I would say my recommendation is always to have a specific project you're working on, which, I mean, if you're at work, you're gonna have. And then start by finding things that are super relevant to that particular project. And then sort of slowly build out from there. Nobody, like, I don't mess with computer vision, y'all. Like, I don't. Or like, I sort of know vaguely about reinforcement learning, but if you were like, build me a reinforcement learning algorithm, I had to go like look stuff up and, you know, basically start from scratch there. So, yeah, nobody expects you to know everything. If they do, then that's on them. It's not a very realistic expectation, and yeah, little baby steps. Faisal says, please suggest the rule policy for tomorrow's session. Yeah, so tomorrow we're going to be back with live coding, same time, 9 a.m. Pacific, and I think we're going to be doing something with an FAQ. I've been thinking about this, which I believe in 2.0 is now part of the rules, so yes. Valzuar says, I'll be working on chatbots. I work on chatbots. Have you tried Rasa? I'll just pull up the docs. Listen, I love the docs. So if you're not familiar, we are an open source framework for building conversational AI. And also we have something called Rasa X, which is a platform that you can host wherever you like to continue your development process and improve your assistant over time, so that it does better. And also we help you handle CI/CD for machine learning, which can be tricksy. Yeah. All right. Robbie says, what about dialect bot? Give that a little break for a little bit. We might get back to it. Anyway, I will see y'all tomorrow morning at 9. And then we will be back next week. I'm taking some time off. I'm trying to remember if I'm actually going to be in on Wednesday. Yeah, okay, so next week there won't be anything on Wednesday. I'm going to be out of office doing stuff. And then on Thursday we'll come back with a new paper for the paper reading group. Great. Thanks for joining me today, everybody. I hope you found this helpful and useful, and give you some food for thought and some methods to use if you're interested in, model explainability. And I will see you all tomorrow.